Okay, first of all, thank you so much for inviting me to be here. It's so good to escape winter in Chicago. I'm going to talk to you a bit about some beyond the standard models that we can search for at the neutrino experiments. Of course, it's impossible to give a fair picture in just 10 minutes, so I'm just going to talk about a few cases which are especially very interesting to myself. But you have heard a bit about the new physics searches we can do in the other neutrino talks that you heard in the last 2-3 days. So I'm going to just mention some dark sectors that we can search for using the neutrino experiments. And I'm also going to tell you how we can use the SMF language to look for new physics at the high energy scales using the neutrino experiments. So at the accelerator neutrino experiments, energetic beams of protons hit targets and they produce lots of charged and neutral mesons. These decay into neutrinos. These neutrinos travel to a near detector, which the goal of these near detectors is mainly to study the systematic uncertainties on the neutrino fluxes. And then they travel to far detectors and oscillation-related parameters of neutrinos would be studied there. But because of the distance of these near detectors to the source of neutrinos, we have a very high statistics of neutrinos at the near detectors. And then also in addition to the charged mesons, we also have neutral mesons that they decay into photons. So in addition to a huge flux of neutrinos at the near detectors, we also have a huge flux of photons. So we can use these huge fluxes to also search for the dark sector because if we have new physics, then these charged and neutral mesons also could decay into the mediators of new physics. They could decay, for example, into heavy neutral leptons or into dark photons, which can also decay into dark matter particles. And then these new physics mediators, they can also travel to the near detector and they can leave some observable signatures. So there are a lot of efforts in the literature using different near detectors of current or future neutrino experiments to search for the dark sector. One of the examples is, looking for axion-like particles. The fluxes of photons can be used to search for ALPS with ALP photon coupling. If we have ALPS and they couple to photons, from the Primakov scattering, we can produce ALPS that they can travel to the detector, and again through inverse Primakov scattering or through the decay of ALPS into a pair of photons, we can be able to study ALPS as well. And for example, at the case of the Dun near detector, we can see that the parameter space of the ALP coupling and mass that the Dun near detector can probe is far better than any current or future lab-based experiments that can be sensitive to the ALP coupling and mass. The same can happen at the reactor neutrino experiments, that they also have a huge flux of photons, which also can be used. So can be used for ALP studies. So we can see there is this cosmological triangle, which traditionally we know is far from the reach of any lab-based experiments, but the neutrino experiments can be sensitive to that. We can also look at the ALP couplings with other particles, for example, ALP-Gluon couplings, and also at the case of Dun, we can see Dun can give the best constraints here. We can also study light Z-prime models at the neutrino experiments, depending on how we allow the Z-prime coupled to what combination of quarks or charged or neutral leptons. We can use different low energy experiments to search for the coupling and mass of the Z-prime. And again, there is a huge literature on this, just focusing on the case of the Dun near detector, for example, on the case of leptophilic, anomaly-free leptophilic models, for example, the model of L-mu minus L tau, we can see that the best current constraint on the parameter space of These can come from the CCFR experiment by looking at the trident neutrino production. From LHC, we can get any sensitivity at masses smaller than a few GeV from low energy colliders like Babar, again masses smaller than a few hundred MeV are unprobed. This model is also very interesting for us because it can explain the G-2 anomaly, but we see that an experiment like Dune can be able to probe the whole parameter space, which can explain the G-2 anomaly by taking a few years of data. These were just two small cases of dark sectors that we can study using the neutrino experiments. But we can also discuss how about high energy new physics. Can neutrino experiments have any access to TeV scale new physics or not? And we want to do that using the language of the effective field theory. Neutrino experiments are usually at a scale much lower than the Z boson mass. The relevant theory at these scales, the relevant effective field theory, is the weak effective field theory. It has the same similar interactions to Fermi-like interactions between leptons and quarks. So if we want to see if we have new 4 Fermi interactions, how we can study these at the neutrino experiments. The relevant effective field theory at the scale higher than the Z boson mass is a SMEF that most of you are familiar with. It has the same particle content and the same local symmetry as the standard model, but we add higher dimensional non-renormalizable operators to the Lagrangian. So if we assume WEFT is the low energy component of a SMEF, by integrating out all the heavy particles of a SMEF, like W, Z, Higgs, and the top quark, we can get the same Lagrangian of WEFT. Then by comparing the parameters of WEFT and SMEF, by matching the parameters of WEFT to SMEF, indirectly using the neutrino experiments, we can get constraints on the SMEF parameters. So the goal is we use the neutrino experiments, we get constraints on the parameters of WEFT, we get constraints on these left-handed, right-handed scalar, pseudo-scalar, and tensor interactions. And once we get the constraints on these epsilon parameters, we can match with the Wilson coefficients of the SMEF Lagrangian, and then we can translate them to a specific beyond the standard models indirectly. So the question is, if we have these new 4 Fermi interactions, how we can study these at the neutrino experiments. These new interactions can change the production, the detection, as well as the oscillation of neutrinos between the source and between the target. So if we know from the theoretical side how exactly we can understand how the fluxes of neutrinos are, and we can study well how the cross-section of neutrinos are in the presence of the new interactions, then we can predict by looking at the expected number of events at the experiment, and by comparison with the observation, we can see how well we can get constraints on these epsilon parameters. Just as an example, for the case of the Fraser-Nu experiment at LHC that you heard at the talk by Felix Killing, the neutrinos at this, for Fraser-Nu, they are produced using different charge and neutral mesons at LHC. So we have different kaon, pion, and d sub s mesons that decay into neutrinos. So we have all the 3 flavors of neutrinos, electron, muon, and tau neutrinos, coming from different combination of mesons, which are sensitive to different up and down type quarks. The detector can then observe all different flavors using the deep elastic scattering. So a combination of all these different production channels, as well as the detection at the Fraser-Nu experiment, gives us the opportunity to probe many different 4 Fermi interactions. Just to show you some results, at the case of the Fraser-Nu experiment and for the case of the pseudo-scalar new physics, the results on the epsilons that we can probe are shown by these colored bars. For each interaction that a neutrino detector can probe, we can always compare what are the constraints from other low energy experiments, for example, beta decay, pion or kaon decay experiments, or from the hadronic tau decays. And we can always compare with what are the constraints that we can get from SMF coming from high energy. And so we can compare the results from the neutrino detectors with the results from other low energy or high energy experiments. Because a neutrino detector has the ability to probe different neutrino flavors, we can be able to probe many different Fermi interactions using a neutrino experiment. For the case of the phasor experiment, in total, we can be able to probe, for example, more than 80 different Fermi interactions for all possible up and down type quarks, for all different charged leptons, and all different flavors of neutrino. We see that, especially for the pseudoscalar interaction, epsilons of the order of 10 to the minus 3 can be probed, which translates to new physics reach of almost 10 TeV. We also see that for some of these epsilon parameters, the constraints we get from a neutrino detector are complementary, or for some cases, even better than the constraints we can get from other low energy or high energy experiments. So the point is that we can study either low energy or high energy new physics using neutrino experiments, and then only by comparing the results with other low or high energy experiments, we can see what is the place of neutrino experiments in the broader program of precision measurements. So to conclude, we can do very interesting new physics searches using neutrino experiments. I showed you a few cases of studying axion-like particles or light Z prime models using neutrino experiments. But our ability is not only probing physics at low energy. Using the neutrino experiments and by entering the precision era, now we have the ability to also study high energy new physics by using the language of the effective field theory at the neutrino experiments. And sometimes we can see that the neutrino experiments can give very valuable or even dominant results compared to high energy experiments. Thanks.
Questions?
Well, Michael Peskin. I'm really confused about what you said about phasor, because I thought that one doesn't actually know the meson production in the forward direction. That's something that one has to measure in this experiment. So how can you know what the source is with which you're convoluting these dimension 6 operators?
This is a perfect question. So here the assumption is we have simulated the fluxes. We know the fluxes. And by assuming that we have a feeling what the fluxes are, then we can do the calculations on dimension 6 operators. But
there's no data that determines these fluxes. This is an entirely new region that's never been explored.
So the idea is when the experiment happens, we will have the fluxes. And only after years of data taking, then we will know what is the standard model fluxes, and we will put these new interactions on top of that.
But you don't know what the mesons are, which are the source of the neutrinos. All you know is the E to mu to tau charge current ratios.
That's true. But the point is that imagine the uncertainty is even of the order of 50%. These results are mostly statistics dominated. So it means that we expect to have of the order of 10 tau neutrinos completely from the theory. And we expect to have of the order of thousands of more neutrinos. So because of the new physics, if the new physics, the new interactions exist, a lot of these electron or muon neutrinos can convert to the tau neutrinos. So the results are mostly mostly statistics dominated. So these colored bars shown here are with different assumptions of systematic uncertainties. Some very optimistic assumptions of like 5, 10, 15%, and some very pessimistic assumptions of up to 50%. And we saw that even though, of course, they change, and this is logarithmic scale, but even though they change by a factor of a few, they don't change by orders of magnitude, because it's mostly from the higher statistics of electron or moon compared to tau neutrinos that we are getting these results.
And I guess I just have to ask you one more question. These fits are with one operator at a time? Or
Yes.
the whole? Yes. Okay. Thank you.
Any other questions?
I guess I've actually got one that maybe follows up on Michael's question. So indeed, if these fits are with one interaction at a time, what happens when you sort of turn on all the interactions and then marginalize in a sort of a combined fit relative to the other constraints from other experiments?
So we never did that because the number of parameters is just too many. And at least computationally, we still don't have the ability to do that. So to be fair, I don't know the answer.
Okay, thanks.
Any questions online? Then let's thank all the speakers of the session.